In this video, I'm going to talk about solutions in greater depth and also talk about something called colligative properties and how to calculate temperature changes dealing with colligative properties. First off, a solution is defined as a homogeneous mixture. And typically in chemistry we're talking about liquid solutions, so like salt water solutions and things like that, so things with liquids. But technically anything can be a solution, whether it's two solids mixed together in a homogeneous mixture or two gases mixed together in a homogeneous mixture. As long as it's a homogeneous mixture, it's a solution. There are two parts to every solution. There is the solute. And the solute is just the stuff that's dissolved in the solution. And then the solvent. And that's the thing that you're dissolving the solute in. The way you can tell these apart is that the solute will always be in the lesser amount and the solvent will always be in the greater amount. There are lots of different ways to measure the concentrations of solutions. The first way I want to talk about is called molarity. Molarity is typically abbreviated with a capital M and is equal to the moles of solute over the liters of the total solution. The second method to measuring concentration is very similar to molarity, except it's called molality. And molality uses a lowercase m as an abbreviation. Molality is the moles of solute per kilogram of solvent. Any equation that has three variables, kind of like this molarity equation where we have one variable here, the second variable here, and the third variable here, we can usually make a triangle for to make the math easier in solving for any of those three variables. And so I'm going to do that for you here. There's something called the molarity triangle. And in this molarity triangle, we put the molarity in the bottom left corner, we put moles at the top, and then we put liters in the bottom right. The way the molarity triangle works is that you cover up the thing that you're looking for. So for example, let's say that we're looking for the liters of the solution. So we would cover this up with our hand, and you can see what that's going to be then is the moles divided by the molarity. So whatever you're looking for, you're going to cover up with your finger or your hand and then do what it tells you to do. So if you're looking for liters, you're going to do moles divided by molarity. If you're looking for moles, you're going to do molarity times liters. If you're looking for molarity, you're going to do moles divided by liters. Because in molarity and molality we're dealing with moles, one of the conversions that we've learned before that's going to be absolutely critical for you to be able to do is changing from grams into moles or moles into grams. And remember, the way we do this is anytime in dimensional analysis you have moles over grams or grams over moles, this whole conversion is called molar mass. And when we're using this conversion, we always put the number 1 next to moles, and then we always actually put the molar mass with grams wherever that is. This term colligative property, what a colligative property really is the property of a liquid when you add a solute to it. So it's how the properties of a liquid may change when you add some sort of a solute to the liquid. The two main colligative properties that we're going to consider at this level of chemistry are called boiling point elevation and freezing point depression. This first one, boiling point elevation, what that means is that when we add a solute to a liquid, it actually increases or elevates the boiling point. For example, if you add salt into water, water will no longer boil at 100 degrees Celsius. It's actually going to boil higher than 100 degrees Celsius. So that's boiling point elevation. For freezing point depression, the freezing point of a liquid is actually going to get depressed or go down. So instead of water freezing at 0 degrees Celsius, if you add salt to it or some other type of solute, it'll actually freeze at a lower temperature. And this concept is used to make ice cream. It's also used to try to melt ice when it's really, really cold outside. It's the reason why they put calcium chloride on the ice outside in order to melt it when it's freezing outside. There are two very similar equations that dictate how far the boiling point will elevate and how far the freezing point will depress. The boiling point elevation formula is that the change in the temperature of the boiling point is going to be this constant called Kb times the molality of the solution. Now the freezing point depression, the amount of temperature that's going to depress, is equal to Kf, which is a slightly different constant, times molality again. Anything with K in chemistry is going to be a constant. So this is called the boiling point constant, and this is called the freezing point constant. And those have to be given to you. They're very solvent dependent. So water, for example, has a Kb and a Kf. Ethanol has a Kb and a Kf. Another solvent called chloroform has a Kb and its own Kf also. Once you figure out this delta T, whether it's for the freezing point depression or the boiling point elevation, the way you use this delta T, or change in temperature, is that you either add it or subtract it from the previous solvent's boiling point or freezing point. So let's say, for example, we know that water boils at 100 degrees Celsius. And let's say that we do a problem where we add salt to it, and we figure out that the delta T is going to be 4 degrees Celsius. What we would do is add this 4 degrees to the old boiling point. So we would say that our new boiling point is 104 degrees Celsius. And similarly, if we're doing a freezing point depression problem and we figure out that the change in temperature is, let's say it's also 4 degrees Celsius, and let's say that the solvent is water. We know that water freezes at 0 degrees Celsius. So instead of adding 4 degrees to this like we did with the boiling point, because it's freezing point depression, we're actually going to subtract the 4 degrees Celsius to find the new freezing point. So that means that the new freezing point of water would be negative 4 degrees Celsius instead of 0 degrees Celsius. Okay, so on this slide, the molality is going to be our moles of solute, the 0.509725 with all the other numbers after it, divided by the kilograms of solvent, which we said was 3 kilograms of solvent. So I get that our molality is 0.1699 with a bunch of other numbers after it again. I'm not going to round at this point because we're still in the middle of a problem. The unit for molality is called molal, which is just abbreviated as a lowercase m. And so now that we know this, we know that the change in the boiling point is going to be Kb times the molality. So the change in the boiling point is going to be 0.52, which it gave us in the problem, times the molality that we just figured out, that we're going to put right there. So 0.1699 with a bunch of other stuff after it. So when I calculate this out, I get that our change in temperature is going to be 0.088. And you can notice here that I've went ahead and rounded it now to 2 sig figs based on this. So there's our 2 sig figs. So 0.088 is the change in our boiling point. But remember, the question was actually asking us for the new boiling point. So once we know the change, we can figure out the new boiling point. And so the new boiling point is going to be the old boiling point, which for water is 100 degrees Celsius, plus, because it's boiling point elevation, 0.88 degrees Celsius. So our new boiling point is 100.88 degrees Celsius. It's important that you don't just stop the problem here and you actually read the problem and realize you're looking for the new boiling point. And then you add that change in temperature to the old boiling point. And if it's of water, you have to remember that the boiling point is 100 and freezing point of water is 0. If it's not water, typically you'll be given the boiling point and the freezing point. So here's our next question. It says if 67.7 grams of sodium sulfate is dissolved in 833 kilograms of chloroform, what is the elevation and boiling point? And it tells us that the Kb of chloroform is 3.85. So remember that our boiling point elevation equation is delta T equals Kb times the molality. And the molality, like before, is the moles of solute divided by kilograms of solvent. This unit really gets a lot of people. You have to remember that it's actually kilograms of solvent, not grams of solvent, but kilograms. Oh, by the way, it looks like I typed that problem wrong. On your sheet, I think it says it's dissolved in 833 grams of chloroform, not 833 kilograms of chloroform. So up here, that should have been grams of chloroform, not kilograms. So let's first figure out the moles of solute. Well, you're going to have to know that sodium sulfate is Na2SO4. And so if we have 67.7 grams of Na2SO4, we need to change that into moles. And we know that anytime we have moles over grams or grams over moles, that's called molar mass. And in molar mass, we always put a 1 next to mole, and we put the actual molar mass next to grams. In this case, we have 2 sodiums plus 1 sulfur plus 4 oxygens, which is going to be 64 total. So when we add all of these up, I get a molar mass of 142.05. So that's the number going down here. So when I do this out, it looks like the number of moles we have is 0.4765927. And again, I'm not going to round this yet because we're in the middle of a problem. So let's go ahead and just keep that whole number and keep on going till the very end. So now we know the moles of solute, and hopefully we can figure out the kilograms of solvent based on the fact that we have 833 grams. What you're going to have to remember is that 1 kilogram is the same thing as 10 to the third grams, or 1,000 grams. So there's 1,000 grams in a kilogram. So if I have 833 grams of chloroform, 1 kilogram is 10 to the third, or 1,000 grams, which means I have 0.833 kilograms. So my molality then is going to be 0.4765927 moles divided by 0.833 kilograms. And so I have 0.57214 with a bunch of other stuff after it, and that's my molality. So remember that the change in temperature is going to be the Kb times the molality. So our delta T is going to be 3.85, which is the Kb of chloroform, times that molality that we just got, the 0.57214 blah blah blah, and I'm keeping that whole number in my calculator. And I'm getting a change in temperature of 2.20. And again, this is where I'm taking my sig figs, because we're pretty close to the end of the problem here. And this number right here is 3 sig figs, which is going to dictate how many sig figs I have for my delta T. And that's degrees Celsius. So there's my final answer there. The boiling point is going to change by about 2.2 degrees Celsius. And it didn't ask us for the new boiling point in this time, which we don't know the boiling point of chloroform, so that would have had to been given to us. All it was asking for is what was the elevation. And this is the elevation. We're actually going up by a little over 2 degrees Celsius.